Hello everyone. Now let us play a game. So imagine this is you, okay, and in this game you are supposed to throw a ball into this region here. If you throw the ball into hole A, you get some money. If you throw the ball into B, you win some cash, or into C you win some cash. So let's say to enter this game, you have to pay, for example, $2. Okay, $2 for one try. And let's say if you manage to throw the ball into hole A, you earn, for example, maybe $1. If you manage to throw into hole B, you win maybe $3. And if you manage to throw the ball into hole C, maybe you earn around $4. So let's say this is the game. So now let me use capital X to represent a discrete random variable. Okay, in this case it represents our winnings. Okay, so for this game, X can be $1, $3, or $4. And we put these values inside our discrete probability distribution table. So the top part represents our winnings, and the below represents the probability of, let's say, winning $1, probability of winning $3, and probability of winning $4. So how do I fill up the probability? Okay, this one is just something, an example. Let's say somebody has played this game before, and that person has played so many times. So maybe he counted the number of times he win $1, $3, and $4, and then he created his own probability. So let's say this little dude, hey man, I've played this game before. The number of the probability that I win $1 is around maybe 11 out of 15. And then the probability I win $3 is around 1/15. And the probability that I win 4 is, okay, you there's no need for me to tell you. You can guess. All the probabilities must add up to give you one whole. So this is actually 3/15. Alright, so this is just my observation of the game that I've played. And now let us calculate the expectation value. Now recall, what is expectation value? Expectation value kind of represents the average. And for expectation value, the probability is as follows. If you can recall this, so it's just the product of X and the probability for each of them, and then you add them up. So let's do this. So I have 1 times 11/15 plus 3 times 1/15 plus 4 times 3/15, and that will give me 26/15, and that is roughly, let me calculate, around $1.73. So in this game, you are expected to win $1.73, and to enter this game you have to pay $2. Now think about this. Will this be a fair game? Is this a fair game? You pay $2, but for this game you are expected to win $1.73. So think about it. Is this a fair game? Okay, the word fair has many interpretations. Alright? Maybe in this case, if I paid $2 and I am expected to win $1.73, it might not be fair. Now, what if somehow the probabilities were to change, and somehow your expected value becomes $2. So you pay $2 and you win $2. Now tell me, is this fair? Now, what if somebody else has played this game? Maybe this guy, hey man, I've played this game before. My probabilities are different, but when I calculate my expectation value, I get around $2.10. So, how do you define a fair game? You paid $2, and at first, we could win on average $1.73. And if let's say somebody else has played the game with different probabilities, and on average he win $2, is that fair? Or maybe somebody else has played the game and somehow his average value is $2.10. So is that a fair game? $2.10 appears as getting a profit, while $1.73 appears to be you getting a loss, and $2 is like you neither win nor lose. So how do you define a fair game? Does a fair game means you get a profit, you get a loss, or you get neither profit nor loss? So how do we define fair game in maths? So if a game is to be fair, alright, and if you were to use simple logic, simple relation, for a game to be fair, there should be an equal chance of winning and an equal chance of losing. That is what makes a game fair. Therefore, you make neither profit nor loss, which means if you had paid $2 for the game, and for the game to be fair, your expected value should also be $2. You neither gain a profit, you neither loss. So what you pay is what you get on average. That is what makes a fair game. Let us now take a slightly different approach. It's the same game, you pay $2 to enter, you only throw the ball once, you can either win $1, $3 or $4. Previously, I let capital X represent my winnings. Okay, now let me do a bit of a slight change. Let X represents the gain. Okay, the how much I gain if I enter this game. So what do I mean by that? If I pay $2, I win $1. What is my gain? Okay, if I pay $2 to enter the game and I win $1, I do not gain, I lost $1. So the gain is -1. I pay $2 to enter and I win $3. How much do I gain? I gain $1. If I enter by paying $2 and I win $4, how much do I gain? I gain $2. So this will be my new X. Okay, my X no longer represent my winnings, but my X represent the gain. Alright? And now I'll put these values inside a probability distribution table as follows. Okay, and for each of the gain there is some probability. Okay, for now it doesn't matter what the probability is. Now tell me, previously we mentioned that in a fair game you neither win nor lose. What you pay is what you get. But right now let's think about the gain. Alright, if this was a fair game, okay, sorry, for a fair game. Alright, what do you think will be the expectation value of my new X now? Okay, remember X now represents the gain, and in a fair game you neither win nor lose. So what do you think will be an expectation value for a fair game when X represents the gain? If you think carefully, okay, and slowly and relate to what we have learned just now, the answer is 0. If X represent the gain, and we know and we want for a fair game you neither win nor lose, so by definition the expectation value should be 0. And thus we conclude with, if X represents the gain from a game, alright, the word here is important, the gain from a game, and if that game is fair, the expectation value of that random variable X will be 0. And this is the important result for this lesson. But let's say the X in the question does not represent winning, it does not represent the gain, but instead represent the winnings from a game. Alright, and for example, if this game you have to pay $2 to play, then to ensure that it is a fair game, it's just to make sure that the expectation value of this X is also $2 for this to be a fair game. I hope you understand this.